All right, so last time we went through this slide set number 4. Then we said that um, this is before the balanced load, right? I'm gonna go here through the example again and try to connect here between the example and between our homework. So in here we have given superimposed dead load on live load, and the self weight was also given. If you look here, self weight was also given to us, right? Where's the self weight? It's right here, 359, and then plus 400. And then we said at the beginning we're going to be applying this FPI, which is 189 KSI at the beginning, right? And then this is going to be like the initial pre-stress. And this initial pre-stress, in a matter of maybe a month or a couple of weeks, is going to drop down to this effective level, the 150 KSI. This is going to be about maybe 15 to 20%. In this course here, usually we're going to be using the 150 KSI in our design as effective stress, and this is going to be the initial stress. Sometimes they call it instantaneous stress or pre-stress, which is fine. Any one of them is going to be acceptable. Now, you apply this, and then all of a sudden you see here the stress is dropping down because the material relaxation of the steel. The steel is going to start to relax a little bit, and also you're going to have this losses in concrete because shrinkage and creep. I'm sure that you guys maybe hear about this term, shrinkage and creep. Shrinkage because the cement is, or any cementitious material is a shrinkage material, which means it's going to shrink, it's going to reduce in size. So when you have this reduction in size and then you have applied axial load on it through the extension of the strand, it means that you're losing some of this strand stretching that you have done to it. So this elongation is going to drop down, it's going to reduce a little bit because the concrete size is going to reduce. Also, you're going to have mechanical losses in the anchorage itself. You're going to have some slippage. So just imagine that you have the strand and then you have the slippage, you have the anchor around it, and then it's going to slide a little bit. So this is what you call here slippage. All of this losses is going to be nearly 20% to 15%. This is the kind of estimate that people use in their design. So first, when you do this initial pre-stress, the concrete is not going to be at 100% of the strength. It's not going to be at F prime C. It's going to be at lower level. And the reason that this is going to happen, I mean, someone's going to say, why don't you wait till the concrete is going to be attaining 100% of the strength? We're going to say simply, we cannot wait for 28 days strengths. We don't have time for that. We need to move faster because the construction bid in the factory is expensive. So you'd like to put a beam, cast the concrete, put the PT after, let's say, a week or less, and then just take it out, move it, and then put the next. So we need the equipment, we need the form, we need the place. So we don't have time to wait for 28 days, and then after that we apply the pre-stress. So at the beginning, we're not going to be at 100% of the concrete strength, which is kind of critical. You wish, of course, that you wait for the full strength of the concrete, and then after that you apply this high strength in the steel, and therefore also is going to be applied in the concrete. So the tricky part is that you apply this 189 KSI in the strand, in the same time the concrete strength is not at the perfect level that you'd like to see it at. Now the stress is going to reduce, it's going to drop down, as I said, maybe over a month. Now the concrete is not yet at the site for installation, because usually what's going to happen in this situation, they're going to keep on storing all of these precast elements, and when you go and pick something, you never know, maybe it has been there for maybe a couple of years, which is very standard. You go to any precaster, you're going to see old elements that you need to pick, you need to buy. Could be maybe a year, maybe a few months old, but it cannot be like this month, for example. This is going to be rare when you find a situation like this. So now when you take this structure member, this beam or double T or whatever that or blank that you're taking here, it is already at the FPE. All the losses has taken place. Now think about when you put it to service. You're going to be taking the structure member, you're going to be installing in the site, you're going to put concrete topping, you're going to do all the connections, And then after you're done with construction, you're gonna put it for service. It's gonna take maybe 6 months during construction. So at the time when you'd like to apply here the service stresses, you're gonna be already at the FPE. So you never try to put FPI with the service level. This will never happen. Doesn't make any sense. So in this example, we said here's the initial condition, and then I put it as number 1. Here's item number 1 analysis, right? So what did we do? We say initial pre-stress condition and the pre-stressing. Cross-section area of the pre-stress strands is the same. It's not going to change. PI is going to be this number, the cross-section area multiplied by 189. PE is going to be times 150. So this is going to be the initial, and this is going to be the final. Per strain. Don't forget that this is going to be per strain, because this here, it takes 153 times 10. So it's going to be per strains. So this is going to be for all the strains, not just per strain. If I just use 0.153 times this stress is going to give me the force per strain. Now this gave me the forces per 10 strains, which means at the end of the day, if you like to use this and put this strain in use, the effective force is going to be 22.95 kips. So effectively, per strain is going to be 22.95 kips per strain. Each strain is going to be taking this number, and this number is easy to remember. So I know it by heart. I mean, just it's about 23 kips. This is the way I would think about it. Now, at the initial condition, I'm going to be jump here to the initial condition. Initial condition, I have PI, initial pre-stress, and I have only the self-weight. So this load is a self-weight. This equation, I have it. It says exactly where to get it from. Maybe the slide number is different, but it's going to be the same set. But you have the equation. Let's give you the bottom line. I have this equation, nice equation for the top stress. Next slide, another equation for the bottom stress. So this is going to be for the top stress, and this is going to be for the bottom stress. This is going to be when? This is going to be at I, initial time, initial pre-stress, initial condition. So what do I have? I have initial pre-stress. I have all the parameters, which means the section parameters of the double T or the beam, and I have only dead load. So at that time, I'm going to be checking here the stress top and bottom. Do I have limits? I'm going to say yes. Now the limits that you're going to be comparing it to, they are all listed here. It says FCI. What's FCI? This is at the time of pre-stressing. When it says I versus nothing like F prime C, it's going to be the difference, right? This one is going to be at the PI, this is going to be at the PE, at the effective. So it says FPI, FCI prime is going to be the concrete strength at the time of the initial pre-stress. So okay, fine. So I'm going to have here stress and compression on the top, and the stress, it could be sometimes in tension or compression, is going to be at the bottom. It depends on the way that I'm going to put the cables and strength.
So where do we get those parameters in the homework, like the CP and the R?
This one, EC,
Yeah.
R?
Yeah.
You calculate yourself. What do you mean?
I thought they were supposed to be given, the CP
given,
and the R.
Okay. Like what I said, in a section like this, is going to be given to you. Because it's going to be a complex section.
Oh, okay. Got it.
But when I give you a rectangular section, like the one I'm going to give you in the exam, I mean, you cannot say, I don't know how to find out the moment of inertia, because you have done it many times for rectangular section and a T section. And they ask you to do a quick spreadsheet to do this for you. And of course, you need to verify it, confirm that it works fine. Not for a case like this, but it's going to be for rectangular section.
Okay, got it.
Here's our problem. Our problem is going to be very simple. Rectangular section. Can you find out the cross-section area? Like all of these parameters, right? Can you find out the cross-section area for this? Yeah, you have done it already. You have a previous homework. It's exactly the same dimension, isn't it? Okay, here's the cross section. Moment of inertia, can you do it? How do you do R? R is going to be what? R squared is going to be moment of inertia divided by the cross-section area. I mean, C bottom and C top is going to be 12 inches, right? Each. Nothing here, I mean, to give it to you. I'm not going to give you all of that. If I give you all of that, it means what do you want from me? Should I also give you the solution, for example, to this problem or to this homework? So it's so simple, right? I guess. I'm just guessing here. So one case, which is initial condition, I'm going to be checking here the stresses top and bottom of the beam or the double T or the precast member. And then after you're done with this, you're going to be doing here the final condition at service. In this case, here's the equation. It looks very similar. Look at this. All the terms are almost the same. The only difference is going to be this PE and MP. That's it. I'm just changing here the condition at the effective time of pre-stress, which means after all the losses, you're going to have here the total service case. So I'm checking here two cases. One of them is going to be at the initial, the other one is going to be at the service, at the effective stress. This is all what you need to do. Was there any question about this 90% and whether that it needs to be close to 90%? Is this 90% what? Max or minimum or what? I mean, do you guys have any question about the first item? Item number 1. Yes, no?
I think
No,
we're
no
good.
questions.
Thank you.
Let me show you this. Here is my quick spreadsheet to do a problem like this. You guys have your homework ready? Maybe you can also grade your homework in the same time. We're doing it here. Yes? No?
Yes.
Would you please have your homework ready, the solution to your homework, and let's go through this and see how it's going to work with us? Can you help me please with this?
Yeah.
Is everybody there? Do you guys hear me?
Yes.
Yes, we can hear you.
Okay,
Yes.
excellent, good. Let me put all of these parameters. I'm going to say the span is 50 feet. Yeah, it says here 50 feet. Cross-section area, 16 by 24. Moment of inertia, BH. This is going to be moment of inertia, right? BH cubed divided by 12, which is the same number here. Again, 16 times 24 times 24 times 24. Okay, it's the same number. Y top and bottom is going to be 12 inches. This top and bottom, this is going to be equal to the moment of inertia divided by this one, Y top and bottom. So, okay. The strand location at the end is going to be at 12 inches from the bottom, right? The strand location is going to be here in the middle. The center of the beam is going to be at 4 inches. Great. This A, how much is this A? The difference between the two, which is eccentricity, or sometimes you call it E, distance from here to there, right? Are you guys with me? Please ask me questions now, if you have any. How much is this distance? I'm going to say from here to there. It's going to be 12 minus 4 is going to be 8 inches. The self-weight, it is 400 pound per linear foot. Is anyone getting the same answer as this self-weight or just me?
Yes.
Yeah. Same.
Yeah.
Same answer.
Okay, great. Additional dead load and life load, it says here 400, right? So it doesn't matter, I can put it all here, I can put it all there, I put 200 here, 200 there, okay? So this section, I guess, we're all in agreement, right? Is everybody reaching the same conclusion I'm reaching here, or any different values?
Professor, the for the service load, like when you give us the superimposed dead load and live load combined at 0.4,
Yeah.
Does that include the self weight?
No, it
Or
doesn't
is that-
include the self weight. It does not include the self weight. Look at this. This is gonna be dead load, right? Superimposed dead load and live load. I put here as 420, right? How about the self weight? Self weight was separate. Where was the self weight? I'm gonna say here's the self weight, 359, completely separate.
Got it. Okay.
So here's the self weight. Did you consider this?
Yeah, I did it separate. I did it separate on the homework.
Okay, all right, that's
I
fine.
was making.
So I can have just done this additional live load. I can just add them together. I'm gonna say here is 400 and here's gonna be 0. That's gonna be getting the same answer, right? Doesn't matter if you put something there, something here. I mean, it doesn't matter. Total additional dead load and live load is gonna be 400 according to this, which is good. Now I'm trying here to balance 90%, and here's also R squared. If someone asks me how to find out R squared, right? This is gonna be this moment of inertia divided by the cross section area. Okay. FPE 150. How do I know it? Yeah, it's given. This is what we are using here, right? For all the strains, we're gonna be using these values. This is gonna be our like standard values. FPI, this is gonna be the 189. So everybody is okay up to here. We're good with this shaded area. Yeah.
Yes.
One strand, it is gonna be 0.153 square inches, which means effectively each one of this strand is gonna be 150 times 0.153. Yeah, I have it here. Look at this. How about PI? This is gonna be for only one strand. It's gonna be equal to 189 times the cross-section area. It's gonna be 28, which means you take each strand and then you're gonna pull it with 28.92 kips. And then after it relaxes a little bit and the losses is gonna drop down to 22.95. So this is gonna be for one strand. I said, okay, good. And here's the equation for it. I made myself very clear on this. How much are you trying to balance again? It says here 90%. So I'm gonna say, okay, 90% of the 400. I'm trying here to balance 360. And I remember that we did this quick math last time. Moment based on this 50 is gonna be equal to this much, W squared divided by 8, right? And also divided by 1,000 to put it in kfoot. This is gonna be the moment for the load that I'm trying to balance. Now, how much is the force needed? I'm gonna be taking this moment divided by the eccentricity, the 8 inches. But be careful here because this is gonna be in kfoot and this is gonna be in inches. So I need a factor here of 12. So I ended up, I need 168. Each strand, this is gonna be effective or this is gonna be what? When you balance this, is this gonna be effective or instantaneous? The initial level. This 168. Is this at the time of pre-stress or this is at the service load? When we do the balance, do we do it at the service load or we do it at the initial pre-stress?
Initial pre-stress.
Where is this? How do you see it here? Just gonna go back to this one here. I'm gonna say this one, we do it by the C line and then we do it by the load balancing method. This P prime, or what is this? It's gonna be at the time of effective, right? At the service level. So it's gonna be P effective. So it's a good thing that we have detailed solved example. So usually if I have a question like this, go directly to your slide set. See when this PE was used or PI was used for the balanced load. I'm doing here, this section or this couple of slides is gonna be for the balanced load. It says here it's gonna be done for PE, which means at the effective, at the service level. So, okay, now I guess it's clear. So this now, it's not gonna be at the initial, it's gonna be at the effective. Meaning that this force that I'm working with here is gonna be the effective force, right? Now take this divided by the effective force per strand. Where's the effective force per strand? It's gonna be this 22.95. I did that, right? It's gonna be 7 point something. But it says here maximum of 90%. If it says here minimum of, it means I need to go to 8 strengths. So I can just change this to 8. But it says here, go to maximum of and be close to 90%. Because if I just say maximum of 90%, someone's gonna say, let me put here 4 strength. 4 strengths should be good. Why? Because I'm within the maximum. I'm lower than the maximum, so I should be good. So I said no, it needs to be 7. Now, how much now is the actual load that you're putting there? I'm gonna say actual load that you put there is gonna be 7 times. Yeah, it's gonna be these 2 numbers, right? And the initial is gonna be this number here. So good. Right after pre-stressing, do you have this equation? Did you guys get these numbers or no? You check the stresses right after applying the pre-stress. Is anyone getting these numbers right after pre-stressing? Can someone help me confirm that my numbers are okay?
I got the same numbers, Professor.
Okay, good. Excellent. Anyone else?
Can you go over those equations for those two? The FT,
For
the
this
FP?
two?
Which equations did you use for those?
Okay, this is right after pre-stressing. So let me put this on. I'm gonna put the slide set, put the example. This is gonna be my reference. At any time, I'm gonna go back to this, just to get know. Right after pre-stressing, I'm looking for this equation that contains F or PI, if you like, FPI or PI. This is here PE, this is gonna be the service, right? M total. This is not the one. This is also PE and M total. No. Okay. This says here final condition. Let me go back. Go back. Right, here we go. This gives me the stress on the top based on the initial pre-stress and only self-weight. That's it. On the top, here's the equation. This gives me the best equation I'd like to use from the example, right? And also I know the reference for it. How about at the bottom? Here it is. Just use these 2 equations.
Professor, I got different numbers for that one actually.
What?
With the same equation.
I'm sorry, say it again. There's some echo in your voice.
I actually got different numbers for FB and FT. Do you want me to tell you them?
So what did you get?
Okay, I got for FT, I got negative 0.45. And
Did you use a dead load?
yeah, I included it in there.
So you use this dead load, right? The self weight of 400.
Let me see. I basically included all the variables, the numbers that I previously got. I just included it in the equation, and then I
Okay.
came out with those numbers.
Okay, Teresa. How about number of strands? Did you use 7?
Yes, sir.
So everything was good, maybe up to here. Just want to confirm. Right?
Yes, sir. Yeah.
Great. Okay. So, okay, anyone else didn't get this answer?
I also didn't get the answer.
Yeah, me too.
Okay, someone else. Someone else who got the same answer. I'd like to see how many people were able to get it correctly.
So, Professor, this one, which part do you solve in?
Which part?
The number you took.
Good question.
Like,
Very good question. It says here, check the stress distribution, top and bottom, right after applying the pre-stress. This is going to be item number 5.
oh, fine.
Did you do it? Ammar.
Yeah, actually, I get like 600, so I don't know, it's too far.
Okay, I'd like to talk to just one person who has done it correctly and was able to get the same answers. All right, I don't have anyone here. Okay, I remember someone said that he got the same answer. All right, so here's what I want you to do, Ammar. I want you here to bring your calculator for quick and start by doing this PI. over AC. The PI value that you're going to be doing is going to be this number, not any other number. Can you help, please, Ammar? I need at least 3 or 4 people to start here with me and to start with their calculators. Take the values from this spreadsheet and please apply this equation. I'd like to see if bottom is correctly or not, is done correctly or not. Now, when you take this PI, is it going to be a positive value or negative value? PI itself.
Positive? Wait.
Is it going to be positive or negative?
Negative.
Negative value. So it's going to be negative multiplied by negative value, correct?
I thought you were saying last week to take the face value of that value that we have. We didn't have to worry about positive or negative.
This is correct. I said that all of these values is going to be numerical values. And this sign is going to curve it. But when I asked about this PI, I got an answer that it was used as negative value. So I want to just confirm, was it used as negative value, PI itself, or PI itself was positive value? For the people, Ammar, please stay with me. It seems that you are fast with your calculator, it seems. So I'd like to prove this. I'd like to prove my numbers here. So can you help, please, with this? Take my numbers from here and apply this equation. Can you help, Chris, please, in this? Okay, go ahead, please.
Professor, what value do we use for the MD again?
MD is going to be this number multiplied by the span squared divided by 8. Which is right here. Yes, Ammar, tell me, what did you get?
Yeah, so Professor, actually I'm in the car, so I don't have the calculator, so it's just
Can you
talking
repeat
and just-
again, please, slowly?
actually I'm in the car, so I don't have the calculator right now.
Okay, great.
Yeah.
Okay, someone
sorry
else
for
who
that.
didn't get the same number. I'd like to hear from you.
I got negative 0.604.
Okay, did you try now this equation with these numbers given here? Did you try
Yes.
it right now?
Yes.
And you're not getting same answer at the bottom, right?
No.
Are you getting something like this?
Yes.
All right. How about the top? Same as here?
Yeah, same number.
Okay. All right. So you're getting this number, right? How many of you
Yes.
guys are getting same as this answer?
Have the same answers.
Me too.
Yes.
Yeah, I got it.
Great. All right. So we're in agreement. This is good. All right. Now let's look at the balanced load. Who get the same answer as this balanced load? This is gonna be for item number 6. How did you do here the balanced load and then the unbalanced load?
I got the same.
Get the same unbalanced load?
Yes, sir.
Okay, so unbalanced load and then unbalanced moment. How about if top and bottom at the balanced? How did you do this?
Is it at negative P over A?
Exactly. So only at the balanced condition is gonna be just P over A. How about at the final, at the service? Anyone getting these two numbers? Top and bottom?
Yes.
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 Okay, 2 people, 3 people, more
Yes.
people? Okay, great. Let's say that all of a sudden I decide here to put 8 strains. What do you think? What's gonna happen to the stresses? I'd like to hear to see your feeling about this. If I'm gonna put lots of strains, what's gonna happen to the top stress at the initial and then also at the service level? This top stress. Let me mark it and put it in, let's say in yellow. Just looking here at the top stress. What's gonna happen to it if I put more strains? Is gonna be more compression on the top or more tension on the top? Or less compression and then a little bit of more tension?
Less compression in the top.
Less or more compression on the top? Less compression,
More.
right? Okay. Now, when you put compression, what would you do? You're going to be bending it up. Because don't forget, the beam loading would bend it down. Your pre-stressing is going to be pushing it up. So let me try this. I'm going to put here 10. Look at this number here. 449 compression and 1.5 compression at the service. I'm going to make this 10. See what happened? How much balancing load that I'm doing here as a percentage? The balanced load is 80%, correct? It's gonna be 80% of the self weight. Once you put 10 here, are you balancing more load than 90%? Look at what happened, 122. So let's say for 7 strains, what's gonna happen? I'm gonna put this here for 7 strains, right? And all of these numbers gonna be making a copy of it. Just numerical values, so we don't lose track of them, right? Now I'm gonna start here to put more strains. I need to reduce this. I don't need to see all of these values, right? It's gonna be too many digits. So I'm gonna put here, let's say 12 strains. Look for 12 strains. What's gonna happen? What happened to the compression? It went down a lot, right? It's close to be 0 stress. How about on the top here also at the surface? It was 1.5 for 7 strains. Now it's gonna be less. So you're pushing it up. How about the balanced load? Now you are balancing more because you put more compression, put more pre-stress. Now you are balancing 147%. Look here at the bottom stress. Bottom stress here, it used to be lots of compression, right? Less compression, like 0.6. Now you start to put more compression at the bottom. Yeah, it went up from 0.6 to 1.7. How about the surface level? At the surface level, we used to have some tension, but now you put lots of compression. Look what happened. You have a little bit of compression. If I made this here, let's say 20, what's the expectation? What's gonna happen here at the top? Would you have tension or you still have some compression?
Tension.
Okay, tension. I'm gonna put here 20. Look what happened. Now I have tension. Look at the balanced load, almost 2.5 times. Look at the bottom. I used to have tension only for 7 strains. Now also now I have high compressive stresses. So actually you can do lots of pre-stressing and you can break the beam even before you start to use it. Because look at these values here. How would you know that the concrete is gonna be able to take all of this tension force? In this case, you need maybe to add some non-pre-stress reinforcing on the top to take all of this tension. Otherwise, you can break the beam. So you can just take the beam, put the pre-stressing, all the beam, all of a sudden just the beam is gone. So the pre-stressing is going to be against the direction of the loading. You guys agree on this, right?
Yes.
Yeah.
Great. Great. Do you guys see this homework? This is going to be now the next homework. Almost everything is the same. It's a 16 by 24, right? Same span, same superimposed dead load on live load, same self weight, same concrete strength, F prime C and F prime CI. But it says here now use 7 strands. So what is new? I mean, this is exactly like our homework, right? Nothing has changed. Look what happened here. It says here, here's the amount of pre-stress force that you have done. PE is going to be equal to this much, 7 times, 22.95. Same thing that you have done. But it says here, during the shipping, they did a mistake. Now, don't forget, this beam here exposed to compression at the bottom, which means it is kind of cambered. It's trying to resist the self-weight and the new load when you apply it, the final service loads. Now, they did a mistake. The crane operator put the beam upside down, which means now this is giving the top and no change for this end. But if you think about the beam now, it's going to look like this. And at the beginning, the strands was like this. Now the strand is going to look like this. If I may bring it from here. It's not good, right? Because actually, this strand is pushing the beam down. So once you apply here again the loads, like the self-weight, this pre-stressing is not helping, it's not trying to balance anything. Actually, it's going to be working to break the beam, to destroy the beam. You guys agree?
Yeah.
In the past, we used to have it like this. And then we said that this pre-stressing is working against the loading. Now it works in the same direction as the loading, which is too bad. This is not good. Now, first question here, to do this analysis, do you need to include the superimposed dead load on live load? You are checking here the beam in the factory at the precast supplier. Now, do you need to do a check here for the service? I can say, no, this is not our problem now. Our problem, would like to see if this beam is still in good shape or not. Otherwise, we're going to trash it. It's not going to be good anymore. So this is going to be the first question. Second question, determine the stresses in the beam top and bottom at the given case. Can I just use this equation? One of these equations or this equation here? Can I use this equation here? Or no?
Can you use it and just put negative?
This is a very good question. Now, what I want you to do in this case is to go back to this presentation. This is going to be the good thing. I mean, this is going to be kind of challenging a little bit. And then you need to understand where is this equation coming from that we have been using. And I said, just use it, right? Look at this equation here. You remember this equation, where it's coming from? And try to figure out what signs that you need to change in your equation. So here's the pre-stressing plus self-weight. You're going to be using these two equations, but something that need to change, that I want you to work on. If you are able to do it, this is going to be perfect. This is great. Now you understand this section. You understand the stresses and direction. Now, after you do here the stress top and bottom, do you think that this beam is going to be in good shape after all of this? So it says here, compare the actual stresses. What do you mean actual stresses? Which means this is stresses. Determine the stresses top and bottom would be the actual stresses. Compared to what? To the allowable ACI stresses. Do you have the allowable ACI stresses? Do you? Do you know about it?
Yeah, on the slide.
Yeah, where's this at?
Somewhere on the slide.
Yeah, like this one. You see this? 6% of FCI. It says right here. because it says less than the allowable. So it is very clear. It is very good here, right? So in compression, I have maximum of this stress. So you need to check the stress here, right? How about in tension? Is there anything about tension stresses or tensile stresses here in concrete allowable? Do you guys see it now?
12 rat.
It's right here. So actually now you're gonna have big problem here with the tensile stresses because now you push the beam down. This pre-stressing is pushing the beam down. It's gonna be causing tensile stress here. And this applied dead load is gonna be also adding tensile stress at the bottom. So the tensile stress at the bottom is gonna be a lot, and then you need to compare it with this number. And the compressive stresses is gonna be also additive from the PT strand and from the given dead load. So also you need to be sure that you're not going beyond this limit, the 6% of F prime CI. How much is this F prime CI in this example, in the one that you've done? I'm gonna say F prime CI is gonna be 4,000 times 60%, as it says here. The limit is gonna be 6%. So take 6% times 4,000. How much is that? 2,400, I guess, right?
Yeah.
So you need to be sure that the stress is not going beyond this limit, these two limits. And in this case, if you're okay, you're gonna say this beam is good. Otherwise, you're gonna say this beam is just bad. It's not gonna work. Any questions before we move to today's lecture?
Professor, can you go back to number 5 from the previous homework? Just I wanted to see what the actual values end up being.
You mean the solution?
Yeah, for the stress.
It's right here. 7 strands, right?
Mhm.
Okay. You're gonna do some comparison with your homework, right? With your solution.
All right, thank you.
Is it close to your numbers or different?
It's a little bit different, but it's probably because I didn't round up pretty good. So
I'm not rounding up here any values. You know, it's just a spreadsheet. So just copying the values, right?
Mhm.
I'm just using it as is. So there is no rounding up.
okay.
So here you have all the values. If you want to back check your answers and your work, you can just go here, right? And it's gonna be all recorded. So I don't really need to post this solution because you can just go there, watch it, and stop right here and look at all the values and confirm that your answers give you the same. All right.
Hey, Professor,
Yes.
should our homework be more detailed than yours? I mean, I think yours is pretty clear, but will we have to make anything more clear? Or is this like this fine?
The way that I put this homework here, it's just to give you the solution and to be able to grade it.
Okay.
So I'm not trying here to show you how to answer it, because in
Okay.
order for you to answer it, you need to follow this example.
Because the way I was doing it was for every part I would put
The
what is
equation,
the equation
right?
I'm using and
Yes,
find
absolutely.
the value.
So you do something like this to show the work. For me, I don't need to show the work for myself. I'm just preparing here the solution for myself, right?
Okay. Yeah.
So very good question, and thank you. Thank you, Steve, for this question.
Yeah, I did the same. I kind of like wrote it out,
Yeah.
but then I can also submit the Excel if that's needed.
No, what I want you to do is to put these equations. And this equation is so simple, right?
Okay, awesome.
And the good thing about this equation is just copy and paste, right? You can do this copy and paste to your spreadsheet. You can just put it there. So it's not really tough.
Yeah, I get that part.
So it is not really lost. I mean, when you think about it, I mean, like this equation, for example, I mean, how long is it going to take for me? I mean, to take me just to type this for quick, or just to do this, you know? I also can do this, you know? I don't know which Adobe you have, but I can do this if I want to, but take it from the black and white, right? Take from the black and white set if you want to. Should I close this? Are we good now with this homework?
Yeah.
Yes.
Good.
Yes.
Thanks.
Very good. And this homework is already posted as number 5. Now let's talk a little bit about materials. Pre-stressing materials. The previous slide set, which is this one here, I put here some material information to you. We said here's going to be the allowable stresses in the strengths. But do you know which strength is this? Well, it says here. If you read the problem, it says here's the initial pre-stress, here's the losses, right? And it says here's this the double T-beam or double T, if you like to call it member. And this is going to be like the allowable stress is 0.45 for the final and 0.6 prime CI for the initial pre-stress. And then I said that this is going to be for certain strengths. And then I said the STM 416. And here's a cross-section area for it and so forth. I'd like to go more in details about this material thing. So you see this 3 slides. This is going to be number 1, number 22 here, the first slide, and the second slide 23, and here's third slide 24, and that's it. Right now I need to go in more details and more depth and explain what we are going to be looking here at. So now the materials. The concrete. The concrete usually ranges from 3,000 to about 6,000. This is what you'd like to use in pre-stress, precast members. In precast members, you're not going to be using 2,500 psi. Only in certain precast members, you're going to be using the 3,000 psi. This can be like if you're buying a volt. You guys know the electric volt, or let's say a catch basin. You guys know what I'm talking about, right? Certain precast elements and members that you can just buy and use there is going to be maybe 3,000 psi at least. No one's going to be using 2,500 psi in the precaster because you'd like to gain lots of strength in a short time, and they're going to be able to use the form again. So it could be maybe 3,000, 4,000 psi at least. When it comes to concrete slabs and concrete members, it's going to be 5,000 to 6,000. This is going to be like the regular concrete. This is not the high strength. If you like to go to high strengths, you're going to be going maybe to 20,000 psi if you want to, maybe 12,000, 14,000. You're going to be seeing this and only precast and pre-stressed. So you don't really need it if you have cast in place concrete or conventional concrete. You don't really need to go to 12,000 psi. But maybe in precast, yeah, there's a good need for it. Now, unit weight for the concrete is going to be 150 for normal weight and 110 for lightweight. And we went through this already. The E sub C, which means the modulus elasticity, this is going to be like the secant value. This secant value is going to be like the slope of this line here. And there's certain recommendations, the ACI code to determine this value here, the E sub C. This slope, the modulus elasticity for the concrete, also is going to be in KSI. We have an equation for it. So the ACI code, the chapter 19, section 12, or article 12, 2.2, not 12, 2.2. They give you this equation here. They say it's going to be equal to the unit weight of the concrete to the power of 1.5 times 33 square root of F prime C, and the whole thing here is going to be in PSI. And they say that this equation is good if the unit weight of concrete, this W sub C, which means gamma sub C, unit weight of concrete, goes between 90 to 160 pound per cubic foot. If you take it as 145, the equation is going to be simplified, and you simply can use this equation here, E sub C equals, which is very common formula that we use in our analysis. Everything here is going to be in PSI, which means F prime C is going to be in PSI. Yes, Chris, you have any questions, Chris?
No, I didn't say anything.
Okay, all right, good. And E sub C itself here, based on this equation, also is going to be in PSI. So if you put this in PSI, this also is going to be in PSI, pound per square inch. Now, this range of concrete strength is also given in this table that we have seen already in one of this earlier slide sets at the beginning. And it shows here that huge is going to be, let's say, 2,500 all the way to 5,000 is going to be very common. It's going to be the conventional, and this is covered here directly by the ACI. How about this concrete strength? When it goes to 6,000, go to 20,000, are we covered by code? I'm going to say yes, we are covered by code, but there is certain other, I'm going to say code sections. It's not going to be the ACI 318, it's going to be different ACI articles or document or codes that covers high strength concrete. So it is covered, but not under the ACI 318, just to make it simple. So under the ACI 318, your max is going to be 5,000 for the size of members. But for any other members, there is no limit. Now they make it open. You have no limits for the concrete strength. All right. Now we have this issue about the initial pre-stress and then the final pre-stress. And we say the tricky part is you apply this high pre-stress force based on 189 KSI in each strand. And you applied on the concrete, that's not 100% at the full strength at 28 days. And this FCI, the initial pre-stress of the concrete, like what was given in this previous homework, was equal to 4,000, while F prime C was equal to 5,000. So I understand that 5,000 at 28 days, but at the time of pre-stress, it was given as 4,000. So my question is, how do you figure out this F prime CI, and after how many days? We have this empirical formula about the strength of the concrete at any time, which means this here is going to be at any time, and it's going to be at the time of applying the pre-stress, compared to the 28-day strength. So this F prime C is going to be the full strength, which is, you can see here, full strength, which is equal to 28-day strength. This is not 28 negative day strength, no, it's going to be the 28-day strength. And this is going to be the strength at any time. Time what? Time t. So here's the time t, this formula. And also this time t. And then we have these two factors, alpha and beta, depends on the cement type. Depends also on the curing. How would you cure the concrete? I'm going to jump here to this slide and come back. Here's my equation again. F prime Ci is going to be equal to T, which is time in days, divided by alpha plus beta, times again T, time in days. For cement type 1, you guys remember cement type 1, which is the same also as cement type 2. It's going to be like the regular conventional concrete cement. And the cement type 3 is going to be the rapid strength. Certain precasters, they'd like to get high strengths quickly, which is going to be creating problem with shrinkage and creep. This is going to be the bad thing about it, but the good thing, you're going to be getting lots of the strengths in short time. So it depends. Are you planning to use cement type 1 or cement type 3? Are you doing this moist cure or steam cure? Why would you do steam cure? Because it can get you also high strengths quickly or quicker. So the curing here time is going to be less. And this is why you're going to be getting lots of strength in short time. Let's look here at the factors, alpha and beta. Here's alpha, here's beta. Alpha and beta, alpha, beta, alpha, beta. Look at these two numbers here. Alpha and beta, 4 and 0.85. This is provided that you're going to be using cement type 1 and you're going to be doing this regular like curing. Conventional curing with just some moisture. you're going to keep the concrete wet. So this number here, alpha is going to be equal to 4 and beta is going to be equal to 0.85. These two values here is going to be where? Denominator here, right? Which means when these two values are large, what's going to happen here for this, for the final value? Because don't forget that the maximum value for this component is going to be equal to what? This maximum of 1.0 max, right? You cannot get concrete higher than the specified. And usually this T, we're going to be using it up to 28 days. Unless you'd like to see how much gain in the strength after the 28 days. But I'm not interested in this. I'm interested only between 0 days to 28 days, because I'd like you to figure out what's going to be appropriate time, right, to apply the pre-stress. So look at this factor here, 4, and then here it drops. If you like to use different cement, it drops to 2.3, because I can just say 4 and 1, the drop down when you use this high or rapid strength cement is going to drop down to 2.3 and 2.7. This makes sense because this denominator here is going to be getting less, which means the whole factor here is going to be higher in a shorter time. So now it makes sense. This factor needs to be less than these two factors. And also compare this to this. 4 to 1. So if you'd like here to do steam cured versus moist cure, the trends in the same day is going to be higher by a factor of 4. Look at this. What happened? Not exactly 4, because you have another component, which is beta times T. But you see here the big difference between the two values. You're going to have higher trends in a very short time once you use this steam cure members versus moist cure. So I guess if you like to gain lots of strength in a very short time, the best way that you do it, you use cement type 3 and then you do steam cure. If you have no problem and the land and the forms are not very expensive, so you're going to be reducing the cost here. You'd like to go to optimize the process. So you're going to be using with cement type 1, which is cheaper than cement type 3. And instead of using this steam cure, they're going to be going with moist cure, which is a cheaper way. So you're going to be staying with these two values, 4 and 0.85. If this is the case, and then you apply 4 and 0.85, it means that you can gain 80% of the full strength after 10 days, which is very typical. This is going to be the standard. Precasters usually they use type cement 1, cement type 1, or cement type 2, which is the same value, right? And in 10 days, they should be able to gain 80% of the trends, and then they can transfer the stress at that time. So 10 days is going to be okay. So now you understand this is going to be maybe 7 days to 10 days. If the precaster doesn't feel that it's here a good idea, he can just do steam cure. It's going to cost him a little bit more. Now I'd like someone here to tell me, in 10 days, how much strength would you gain if you use cement type 1 in the steam cure? What ratio are we talking about? Can you help me here, please? How much is F prime C? In 10 days. Does make sense, right? If you put here 10 divided by 1 plus 0.95 times 10, it's going to be 95%.
95%.
Yeah, wow, this 95%. So I'm going to say 0.95 times F prime C. So how about if I put it as 4 days? You can say after 4 days, what trends would you get?
%.
I guess this is close to this 8. right? 80%. So actually, in 3 to 4 days, and do steam cured is going to be a very good idea, right? And they are going to be at 80% of the trends. So you don't really need to wait for 1 more week, because if I can do this in 3 to 4 days, I don't really need to 10 days to gain 80% of the strength. So I guess now I can do maybe cost estimate or value engineering to figure out what is the steam cured process is going to help me with. It's going to save you about a week. So the question is, does it make sense to use steam cure versus moist cure or not? You can decide on this. You have some tools here. This equation is a very good equation, and you can use it for any of the cement types and for the steam cure versus moist cure. Any questions on the equation?
So like if you do 3, then you're like at like 70, almost 78%.
Yeah.
Is that too low?
No, this is okay. Now you're going to be taking this F prime CI, right? And then, as you said here, 3 day. So let me put it down. 3 days strength is going to be how much? You said 0.078?
7.8. Yeah.
Yeah, F prime C.
70.
Just when you do your analysis, you need to be careful, right? Because the allowable stress is going to be a factor of this, of the entire F prime CI. It's going to be 60% of it, right? So be sure that you're not pushing it. Now, someone says, I'd like to do it in the same day. So I said, well, why don't you go here? Now tell me, how about here? How about after 1 day? How much strength would you gain? Cement type 3, steam cured. 0.6. 2 days, you're done. 2 days, you should be done, right?
.75.
75.
Yeah. So the steam cures gave me the way, right? In 2 days, you should be good. Usually precaster would like to go for 2 to 3 days. And if you watch any videos, you're gonna be listening to this, you're gonna be hearing it. They're gonna say 3rd, 4th day, try to get rid of the concrete because we need the bed to cast new concrete. So we cannot wait. So we spend the money, a little bit more money, and do the steam cure system.
Professor, you said the cement type 3 for moist cure it's much faster, right?
The cement type 3, generally speaking, when you talk about cement type 3, they call it rapid strength. Rapid strength cement. Let me put an old slide set here for you. This is going to be the first slide set. Let's go here to types of cement. Give me a second. Let's give you right here the conventional concrete design, types of cement. Where is that? I remember it was here. Here we go. Cement type 3. Early strength is needed. All right, this gave you type 3. Type 1 and type 2, they called like general use. This is like the cheap cement, the regular cement that you use. Okay? So just by switching from type 1 to type 3, it means that you're going to be going here to rapid strength or high strength. You gain here high strength in short of time, and look at the factors, right? You do the steam curing for whatever cement, you're going to, of course, reducing the time to gain the same strength. So this can be very common here that you're in 3 to 4 days that you're going to be doing the pre-stressing. But you got to be careful because you need to do your checks. What's the check that you're going to be doing here? Again, you need to check in the compressive stresses and tensile stresses. Now you have a prime CI that you just calculate out and then go back to your analysis and be sure that you're not going beyond 6% of this when it comes to the compression, and 12 screw to the prime C if you're allowing any tension in the beam. allowing tension, which means sometimes people design pre-stress to be on crack or crack. So it depends on your target, performance target. Now we're talking about losses. Now we need to know where the losses come from. The first source of losses is going to come from the concrete. Concrete as a material is going to shrink. So we call this shrinkage. So here's the shrinkage. The cement itself is going to shrink. The aggregate is not going to shrink. The aggregate is going to be made of solid rock. And solid rock will not shrink that much. Shrink is almost nothing. So all the shrink is going to happen within the cement. So when you have lots of aggregate, the amount of shrinkage is going to drop down. When you have less aggregate and you have lots of cement, the shrinkage is going to be a lot. So we're not happy with the shrinkage. And also this creep. What's the creep? Creep means it's going to be deformation of the concrete under sustained load, which means under the same constant load. Without changing the load value, just over time, you're going to have more changes, more strains. Let me look here at this curve and try to understand it more. The strain is shown here in the y-axis, and it says a micro strain. So the strain, I understand the strain. And in the x-axis, give you time in days. So this give you time in days. You look at this and say 20 days, 40 days, 60 days, and so forth. At the 0 day, once you apply here the force, whatever forces that you apply to the concrete, you're going to be gaining all of the strain. And this strain is going to be elastic strain. If you bring here a concrete member, apply some force, let's say that the size of the concrete member is going to start to get shorter. In the same day, if you take the load off, which means that you do unloading, we call this unloading. So we have loading and unloading. So if you do unloading in the same day, you can just get back to the same size of the member. There is no permanent change in the size of the member. Now we apply the load, let's say 100 kips in a small cylinder or concrete block. Then you put this 100 kips, it's going to get shorter, let's say by this amount, you're going to have this much strain. Now take this load out, it's going to go back to the same size. There is no change here, permanent change. But if you leave this load, let's say this 100 kips on this big block, if you leave it there, what's going to happen? Over time, you're going to see here that the size is changing of the structure member, even though that you're not changing the axial load. So axial load now is constant. It's going to be this 100 kips. But you leave the load right there on the top of this concrete member. Now the size is going to be changing over time without change in the load itself. That's what we call here creep. So this amount of strain that happens above the elastic strain, so I'm going to say here's the elastic strain line, right? And this can be the amount of elastic strain going to be taken this line, can say from here to there. Give you the amount of elastic strain. It's not good. It's not helping. Anyways. So this gonna be all the creep strain, and this gonna be the elastic strain. At that point, at any point here, if you just draw a line like this gonna be the total strain. So total strain is gonna be all the way from here to there, right? It's gonna be the amount of total strain. And this total strain, which means this ordinate, is gonna be composed of some elastic strain, which is the same value throughout, plus the creep strain that keep on increasing. Let's say after 90 days, you decide to take the load out. So you did here unloading. Look what happened. Once you unload, this elastic strain is going to be coming down. So this amount of elastic strain in the unloading, we're going to call this elastic recovery. So this amount of strain, which is about 220 or 230, is going to be taken out. Because what happened? You have just taken the load out. Some of this creep recovery, which means the strain due to creep, you're going to be recovering it. You're going to be taking back the concrete member size is going to start to go back to the original size slowly. But you're going to be having usually sum of locked strain. So I'm gonna say the strain here is gonna be kind of, this amount is gonna be locked in, and this gonna be permanent strain from here to there. It's gonna stay there, which is not good. So just imagine here you have this precast member, you have the beam, you put here the compression force on it. You are not changing the compression force. Actually, the compression force is gonna reduce a little bit because of the losses, right? But you should expect that you're gonna have some elastic strains, elastic shortening in the beam itself. And just because the creep effect, this beam is going to get shorter and shorter with time under this constant load. So when you do your analysis here, you take P over A, PA, let's say PL divided by EA to figure out the amount of the strain in the concrete is going to be this elastic strain. And in this case, you ignore all of this creep strain, which is not good. This creep and shrinkage, this is just about the creep. The shrinkage, we're going to be addressing it very soon. It's going to be very important that you need to address it when you do the pre-stress losses. Again, this is going to be what? This is going to be the creep. You're going to have elastic shortening, which is this instantaneous strain. This is going to be the elastic strain. This is going to be the creep. At any point here, I can come and draw a horizontal line. I'm going to say here's the total strain from this point to that point. It has two components. One of them is going to be this elastic strain, and the other one is going to be what? This value here. Actually, the elastic strain, yeah. And this value here is going to be the what? The creep. Once you take the load out, you can gain this back, and then you're going to have this delayed recovery, which is a creep recovery. And you're going to usually have this permanent or locked in strain, which means the concrete member cannot gain back its original size. Now, how about the shrinkage? We have this graph for the shrinkage. Here is the strain due to shrinkage, and here's time. It goes fast at the beginning till you hit certain time. After that, it's going to be kind of constant. So why would the concrete shrink? I'm going to say because the cement is the shrinkage material. We have non-shrink material, and of course, we have the shrink material. Cement is, generally speaking, a shrink material. If you put lots of aggregate, what's going to happen to the shrinkage? As I said, you put this rock, lots of rock, the shrinkage is going to be less. You put less rock, the shrinkage is going to be more. Let's say with this water cement ratio, which is very common, the 45% water to cement ratio in any concrete mix, maybe 40% in some cases. Look what happened to the amount of shrinkage. If you have the aggregate by content, right? Here's the content of the aggregate. 80% of the volume, look at the amount of shrinkage. If you have 60%, here's the amount of shrinkage. Big difference.
Professor, when you use larger aggregate in concrete,
yes,
you get like less surface area of the aggregate, right?
When you use larger one, yes, you get less.
Yeah. So does that mean that it weakens the concrete?
When you go to smaller aggregate size, you're gonna have bigger surface area, right? And the effect of the aggregate itself to reduce the shrinkage is gonna be higher. When you put big pieces of aggregate, you're gonna have more cement masses. So the cement itself is gonna be like clusters. It's gonna be big, right? And the shrinkage of it is gonna be larger, because the shrinkage is actually based on the size of the cement. Generally speaking, any shrinkage is gonna be based on the size of the structure member, of the concrete member. So if you have, let's say, a block or a cube, 12 by 12 by 12. Now look at the amount of shrinkage that happened in there. Now compare it with 2 feet by 2 feet by 2 feet, like 24 inch by 24 inch by 24 inch. Same aggregate distribution or grading, and same percentage of the aggregate. You're gonna see that the 24 by 24 is gonna be gaining more shrinkage, right? So it depends about the mass, depends on the mass of the cement that you have in there. So when you go to the same, no problem. When you go with the same volume of the aggregate, but the aggregate itself, the maximum aggregate size is gonna be smaller, it means that you have gonna have more aggregate in the mix. with the surface area. And the amount of cement clustered to each other is going to be smaller. And the shrink is going to be less. It's not going to be much less. It's going to help. The real factor here is going to be the amount of aggregate that you're going to have it here by percentage as in terms of volume. This is going to be the key factor. And also the water cement ratio. Just work here with the water cement ratio. You put lots of water. Concrete workability is going to be very good, right? It's going to be the best if you go to 50% or maybe a little bit higher. But guess what? This is going to be too bad when it comes to shrinkage. So when you add more water to the cement, you're going to be increasing the shrinkage. Not very good when it comes to pre-stress. So actually in pre-stress, you like to keep it maybe 40%. And because it's going to be very hard to work with the concrete with this water cement ratio, you're going to be adding more additives for workability. You can have maybe air entrained. You can have other means or methods to increase the workability of the concrete. But with this, you're going to be reducing, let's say for the same 60%, look what happened here for the shrinkage. Shrinkage is going to drop down just because you reduce the amount of water cement. And all of this is going to be contributing to the pre-stress losses. You remember this 189 that you're going to drop it to 150? This is all based on all of these factors. And we say it's going to be 15 to 20%. Now we're going to be going through all of this factor and see how can we reduce the amount of shrinkage and creep and the amount of losses in the pre-stressing strength. Size of the concrete member is going to be affecting the shrinkage. When the concrete member is large, you're going to have what? More shrinkage. How about the ambient condition, like the temperature and the humidity? What's going to happen there? If it's going to be more humid versus dry, which one do you think is going to be affecting the concrete shrinkage? You're going to say if this is going to be dry condition, of course, I'm going to have more shrinkage. Makes sense. Amount of reinforcement. You put more reinforcing is going to help against cracks, against shrinkage, right? Because the reinforcing is going to keep the size of the concrete member. So now the concrete wants to shrink, but you have the rebars to keep it in place because rebar is not going to shrink for any drying process or for any, creep. It's going to be much less than concrete. Admixtures, generally speaking, it depends. Sometimes you add this admixtures, it's going to be reducing the amount of water, and in this case, it's going to be reducing the shrinkage. But certain admixtures is going to be accelerate the strength, and it's going to be causing more shrinkage. Also, the type of cement. Compare now type of cement 1 versus 3. Cement type 1 is cheaper. It doesn't gain lots of strength in a short time, but also doesn't shrink a lot. You'd like to gain higher strength in a short time, you need to pay with the other hand. If you're gaining with one hand, you need to pay with the other hand, right? So you gain higher strength in a short time, you need to pay for this. It's going to be more shrinkage. There's something needs to be paid. You cannot just get the best and it's going to be, let's say, the same price and everything is the same. This would never happen. There's usually plus and minus, positive and negatives and everything that you're going to be picking here in terms of material. The carbonation here, this is going to be this reaction between the cement and between the water and between this carbon monoxide, carbon dioxide. And this is going to be like, this is going to be the carbonation is a process of the cement hydration and all of that. This is like the cement effect, actually, this carbonation. Now, the total strain is going to happen. The concrete is going to be composed here of 3 parts or 3 components. One of them is going to be the elastic strain. You put this compressive stress on the concrete on both ends, you're going to be shrinking the size. So we're going to be calling this going to be the elastic strain. It's going to be the first component of losses, that the concrete size wants to change under this compressive load. Number 2, the creep. And when through the creep, we understand what does mean by creep. Just under this constant load, you're going to have shrinkage, more shrinkage in the concrete. It's not really shrinkage, but it's going to be changing the size. You're going to have more additional strains in the concrete member. Plus the dry end shrinkage. I'd like to call this dry end shrinkage. When the concrete wants to dry and this carbonation is going to happen and the cement is going to be hydrated, this is what's going to happen. The size of it is going to reduce. Here's a quick example here. Some concrete member exposed to 900 psi in compression, and here was going to happen. Just quick example to understand which factor is really critical to you. Amount of the immediate elastic strain is going to be about 250. It says here micro strain, right? For the shrinkage, in 1 year is going to be about 500, and the creep is going to be 750. Can you cut down this immediate elastic strain by any means? Yes? No?
No.
Okay, when you increase the concrete strength, would that reduce the amount of elastic strain?
Yes.
Okay, the strain equals P times L divided by EA, correct? You guys know this equation.
Yes.
The strain equals the axial load that you cannot change, the length of the member you cannot change, the cross-section area you cannot change for a given member. But the thing that you can change is give you the concrete strength. And once you change it, you can change this E, which is E sub C. This give you the same as this, right? This one here. So once you go here to high strength concrete, you're going to have less elastic strain. So to work on this issue, maybe you go to stronger concrete, which we do in pre-stress. This is one of the reasons that you go to 5,000 or 6,000 psi. How about for shrinkage? What can reduce the shrinkage?
The type of cement you're using?
Water cement, reduce the water cement, which means the concrete mix design, right? Reduce the amount of water to cement ratio. Use more aggregate. Try to use 70% or 80%. Don't go to 6%. And with that, you can get lots. So, I mean, you can reduce the shrinkage by a lot. Look at this. You can use 60 with 45%, which is very common. You can get over 1,200 microstrain. But a good idea maybe to go to 80% and try to go to 0.4. Look what happened. How much did you cut? A lot. Maybe a quarter. It's worth it, isn't it? So it's going to be all about the concrete mix that you use here. So don't use the same concrete mix that you use in conventional concrete in cast in place. Try to be creative and pick the right concrete mix. So usually precasters, they have their own mix design. And of course, they do testing on the shrinkage to be sure that the amount of shrinkage of this concrete mix is low. They call it low shrinkage properties or characteristics of the concrete mix.
Professor, I have a question.
Yes.
So I spent a couple years in masonry, and I know this is like a smaller application for concrete, but you know, a lot of times in the mortar, especially like in wet conditions and stuff, we would use like an adhesive that we would add to the concrete.
To the mortar,
Yeah, I
not
was just
the grout. You're talking about the mortar between the blocks, not the grout, right?
Yeah, like mortar.
Mortar that you
Now I was
connect
wondering
blocks to each other.
Or something, is there like an adhesive or something that you can add it to concrete that has that kind of has an effect where it doesn't shrink as much?
It depends on the type of adhesive that you use. Is it adhesive like that you bind cartridge and then you add it to it? Or this is like something that comes?
It was like in a bottle. It looked like Elmer's glue. It was like this white,
okay.
it was just like glue. You just add it to the concrete.
Yeah, generally speaking, there are certain additives that you add to the mortar to gain high strength in short time. Because usually with masons, as you know, that you like to put the block wall and you'd like to grout. You want to grout, right? Maybe next day if you can, right?
Yeah.
And the problem is the stability of the wall itself. And of course, you don't want to short the wall. You don't want to brace it because it's going to be additional cost. Correct? And also, you're going to be concerned if you're going to be going more than 4 feet for a lift, right? Usually, it's going to be the 4 feet. This is what the code says, maximum 4 feet for the lift. So once you start to pump the grout, you can just explode the bottom block, which is too bad. You don't want to do this, right? So what people tend to do is to secure the bottom 2 blocks, put some shoring or some bracing there. You put some piece of wood and try to brace it. And then there's certain product that you can bring, you can buy it like it looks like a tie. It's like a mesh that you put between lifts. I don't know if you have seen this or not. Like a wire, you put a wire in the mortar. And also there is certain product that you add here to the mortar itself to make it a little bit stronger and to gain higher strength in just one day. So this can be one of them, which is acceptable. And in the mortar mix design, the mortar also has a mix design. Just for the masonry, there's a mix design for the mortar and also mix design for the ground. Right? So in the mix design itself, you can specify any additive to it if you want to. Does it make sense or no?
Yes. Yeah.
Yeah. Okay. Good. So the way about the shrinkage is to control your mix design to reduce low shrink concrete if you can. The creep is going to be the same because stronger concrete is going to have less creep. And also the atmosphere, the surrounding of it, the environment, the amount of moisture that you have around it. And this is one thing that you cannot really control. Like in the shrinkage, the ambient, the rate of humidity, you cannot really change this. I mean, there is no other way. But you can control it by adding different aggregate. So when you add high strength aggregate, it's going to help you out. Excuse me. It's going to help out. When the aggregate is going to be stronger, and when it's going to be well graded, it's going to reduce the amount of shrinkage and creep. Now let's talk about the pre-stressing reinforcement. What are we talking about here? Then we said we have three types. First, we have wires. And the wires going to be very thin, very small diameter. And then we bring a few wires together and twist them all as in one piece. We can have a strand. So the strand is not like a rebar. The strand is going to be a bunch of wires. And they're going to be twisting and put them all together. And also we have some bars, like regular bars of high strength, and you can use it in pre-stressing. This is not very common. It has certain application. So this is not like for concrete slabs. No, we don't use bars. For beams, we don't use bars. For double T's, we don't use bars. So this bars, high strength bars, there's certain applications for it. And usually this is going to be post-tension. But both of these two wires and strands is going to be post-tension and pre-tension. Wires is going to be very common when it comes to pre-tension. So precasters in their yards, they'd like to use these wires. And also strands. If you're going to do here post-tension, most likely it's going to be strands. And in certain applications, it's going to be maybe bars. And this bar is going to be a big bar. This is not a small bar. This is going to be a good size bar. Like this Duodec bar. There's the famous Duodec bar for pre-stressing. So the very common one that usually uses is going to be the strands. And we're going to be using the strands, just The strand that we're going to be using usually is going to be called ASTM A416. And it's going to have a strength of 270, the ultimate. 270 KSI. So here we go. The strand is going to be 416. The wire is going to be 421. So what you do here, you take the 421, you put them as a bunch together, like 7 strands, and then you twist them, and then you make the 416. The higher strength bar is going to be called A722. We're not going to be using this. We're not going to be using the 421, but usually in our analysis, our design, we're going to be using the 416. Okay, good. How would you do here the 416 out of the 421? So first, here's the base material. You have this round bar. You're going to be patting it. You're going to be heating it to high temperature and then let it cool slowly because you'd like to relieve all the stresses out of it. And then after that, you're going to be pushing it through a die. So once you do this, you put lots of pressure on it because in order for you to pull it, you need to put lots of pressure. Look at the picture here. I guess it makes sense, right? When you look at this picture, you're going to be pulling it out this way. You're going to make it smaller. And same time, you're going to be putting lots of pressure on it. You put compression. You're going to be compacting the material itself. Now, after this, you're going to be bringing like one in the middle. You're going to have one of these in the middle, and then you're going to have 6 wires around it. and then you're going to be twisting it. Once you do this, you're going to have a strand. So the strand is going to be called 416. So this is going to be the 421 after you're done with this cold drawing. And then you put it, you make stranding, they call this process is stranding, which means that you're going to put 7 together, and then you're going to be twisting it, and with that you're going to be getting strands, the 416. The 416 here has 2 types. You can just do stress relief, and the stress relief here, you heat it to 660, and then you let it cool slowly. Or you can increase the temperature to 660, you heat it to 660, and then you put tension on it, and then you let it cool down. This one here is called stress relieved. Now we have taken all the stresses out of it. Any stored, any residual stresses, you're going to be getting rid of. But this one here, once you put tension, you heat it and let it cool down, the amount of elongation or permanent elongation or relaxation is going to happen to the rebar is going to be much less. It's called here strand, not rebar. This process here, as you know, the losses, if I need to go back here and talk about the losses in the strands and in the tendons, loss is going to happen because the 2 components. One of them is going to be the concrete. You're going to have strains in the concrete. You're going to have shrinkage. You're going to have creep strain, and also you're going to have this elastic strain, which means instantaneous strain. So one component is going to be the concrete. It wants to come down inside. It wants to get smaller. And for it to get smaller, you're going to have some losses because you're going to be losing the strains, the amount of tension that you put to the strains. It's going to be one component of concrete. Other components going to be about the steel. The problem with the steel, you put tension on it, and all of a sudden you feel that after you put this tension, and then you have this instantaneous strains, and then after that the steel is going to relax by itself. It's going to be just slowly, you're going to be losing all the strains that you put in there, all of the tension. Because of this relax, they call it steel relaxation. This process here of heating it and put it under tension is going to reduce the amount of relaxation that may happen for this pre-stress strain. This is going to be the famous 7-wire strands. We call this going to be the strands, the 416. And as you see here, one's going to be right in the middle, and then you're going to see 6 around. It's going to be all twisted. And this is the way that they do it. And most likely, this is going to be the one that we use in our design. So the one that we used in the previous example, in the previous slide set, was actually 1/2 inch, right? This is going to be like 1/2 inch. 7-wire strain. It's going to be like this. So where's the 1/2 inch? 1/2 inch is going to be like this. From here to there, it's going to be 1/2 inch. How about the cross-section area for one strain? Anyone remembers?
0.153.
153. Range. This is for what? 1/2 inch? 1/2 inch, right? Diameter? Am I correct?
Correct.
How about for the regular rebars? For 1/2 inch. How much is AS? For number, what is this? This number 4, right? Number 4 rebar, how much is AS for it? Anyone recalls the value? Yes? Yes, 0.2 square inches. So in a solid rebar, you're going to have 0.2 square inches. In this type of strands, you're going to have cross-section area of 0.153. Now it makes sense, right? You see the difference here because of this voids here. This is why there is another type of strands that after they're done with it, they start to put pressure on it. They're going to start to compress it. You want to compact it all together. And look what happened here for 1/2 inch. Look at the cross-section area. It becomes here 0.174. And instead of 0.153, you can make it 0.174, but for that, you're going to be using different ASTM, designation. We're not going to be doing this. So usually the one that we're going to be doing is going to be the 416, right? Which is this guy here. There's going to be just a strand. There's going to be twisted wires, 7-wire strand, right? You call it, this is the official name of it, 7-wire strand. So it's going to be made out of 7 wires. And the total cross-section area for all the wires, effective cross-section area, is going to be the one that you use in your analysis. It's going to be 0.153. Let's look here at these two tables for the A421 for the wires and for this 7-wire strand. Look at this name here, 7-wire strand, right? And the grade that we're going to be using is going to be only grade 270. We're not going to be using here grade 250. And most likely we're going to be using the 1/2 inch, which is this guy here. It's going to be 0.153. You can also have in this table, you have the amount of, let's say, the weight per 1,000 feet and so forth. So you know the weight, not really critical to us. What we care about is going to be this value here, the 0.153 in our analysis. 421, not going to be using it a lot, but here's the size of the diameter of the wire, right? And look at the cross-section area of it. It's going to be very small, right? Again, the 779, we're not going to be using it, but you understand the process. You see the pressure, they put pressure on it, they kind of compact it all together to increase the cross-section area of it. Not very critical to us, we're not going to be using it. Now the rebars. If you recall the rebars, I told you like duodec bars. It's going to be usually large size. It starts at what? 0.75, 3/4 of an inch. The very famous size that people would use outside is going to be this guy here. 1.375, 1 3/8 inch. It's going to be a good size, right? To use. Very famous. They call this duodec bars. For the forward bars, you have 3 sizes, like you have almost like 5/8. You have 1 inch, 1 1/4. And of course, the strength of it is going to be high strength. Look at this. FPU is going to be equal to how much? For this grade, 145 and 160. So it's kind of stronger than regular rebars. Our conventional rebars takes about 60 KSI, maybe 75 KSI, but not like 160, right? But the strands that we use here, as we have discussed, is going to be grade 270, which is worth it, right? You need to add something like strong like this. For a 1/2 inch, it makes sense. All right. So again, here's a copy and paste from the code, from the ACI for FPU. We're going to be using this, the 270. This is ours. We're not going to be using this 250. I don't need it. I don't need this 150. So usually all our examples is going to be based on 270 and A416, ACM 416. Look here, some difference between the 416 and between 270 and 250, the performance, which one is going to be yielding first, about the trends, and compare the stress-strain relationship. And look at the big difference between the three. Look also at the 722. Is it 722? Yeah. Look what happened, this pre-stressing. This is going to be like the conventional rebars. It goes here to about 60 for F sub Y, and then goes maybe to maximum of 90 or 100. Compared to this one, like this duodec bars. Quite some difference here. Now, there were 3 values that we have discussed in the previous slide set. We said the ultimate strength is 270 KSI. Also, we said FPI, which means the stress at the initial pre-stress, is going to be 189 KSI. We said the effective is going to be how much? Anyone recalls? How much was the effective pre-stress?
Was it 150,000?
Yeah, 150. This is correct. Here are the 3 numbers that we discussed. 270, 189, and 150. They said here the yield strength is going to be about 229 and 500 psi. This is going to be the yield strength. But when you look at this straight line relationship, you don't really see yield, right? So this yield is going to be based on something that you call here offset of 2%. What they do here, they come and then they draw something parallel to this, right? This give you the secant modulus, and then they do it as 2% offset, and then you just find out where the yield point is going to be at. So this is not really like a good yield point that you see here, because it's going to be high strength material. It's going to be high strength strengths, right? So based on this table here, you said for the stress relieved strength versus the low relaxation, which one you think is going to be good or higher in value? Which one is going to be helping you more? The first or the second? The stress relieved or the low relaxation? Yeah? Which one do you think is going to have higher losses? The low relaxation or the stress relief?
The low one, probably.
This one here is going to have less losses,
Oh.
because this one here, what's going to happen, you spend more money on it. Think about it this way. Let me go back here. In this one here, for the stress relief, you just heat it up and then let it cool down. You don't do anything to it. But look at this one. You heat it up while you are putting tension on it. There's more work, more effort that you put here. And this effort, you don't just put it because there's nothing else to do, right? You do this because this process is going to help you out to reduce the amount of relaxation of the steel. Relaxation means what? When you reduce the relaxation, it means that you reduce the amount of losses that you're going to have in the pre-stress. So this process here is going to be reducing the losses. So when I look at this, it gives you here a ratio between the yield point and the ultimate point. Say yield to ultimate is going to be more than 85%. So the yield point is going to be about roughly maybe 85%, maybe 90% of the ultimate. And for the low relaxation, it's going to be about 90%. So fine. Let me look here. If I use 85% for the 416, don't forget, I'm going to be working here with the 416. When you take here 85% of FPU, because I know that FPU is going to be equal to 270. How do I know it? Because I picked here 416. It says here 270 grade. Now I'd like to figure out how much is this yield point for the 416, the stress relief strength. I'm going to be taking here 85% of the 270. It turned to be 229. So now I know where is this coming from, right? This 229 is coming from here, because simply I use the code value of 85%. I know for sure that I'm going to be using this 189. So what does it mean by 189? It means 82% of the yield point. You see this? 82% of the yield point is going to get you 189. So actually, we're applying pressure of 82% of the yield point, which is 70%. This also 189 is 70% of the full 270. You see this? 70% of the 270, right? It's going to get you to this 189. So this FPI at the time of the pre-stressing is going to be equal to 189, and this 189 is 82% of the yield, which is also 70% of the ultimate. And I know for sure this is going to be dropping down to 150. So 150 is going to be like the lower bound that I'd like to use. I don't want to go more than this. Now someone's going to say, now we have the two components, right? Now we have the concrete. We know how much strain loss that we're going to be having there. And then we have also the steel. And here's what happened to the steel, right? We're going to have FPI, FPE. But how did you get from the 189 to 150? How much loss are we talking about? Yeah, excuse me. The losses here is given by this equation. And this equation is kind of empirical formula here. And this is steel relaxation. This give you the formula that you are going to be using, right? Look at this. It says delta FR. This give you the losses. For which wires and strengths? This is going to be for the normal relaxation, which means the 416, the stress relief type. This is not going to be the low relaxation. So again, we have here two types. If I may go back here, we have two types. We're going to have the stress relief, and then we're going to have the low relaxation strengths. So I'm talking about this one here. This one here, I'm going to have similar equation, but it's going to be giving you lower strain losses, if you like, or lower relaxation. So let me move forward to this. It's going to be based on the initial pre-stress stresses that you put in there, FPI. Let's say the 189. So you can use this as 189. And this term here, it has to be lower than 1 because you're talking here about losses. The amount of losses, it needs to be a small number. You don't want this number to be big, right? It's going to be equal to FPI divided by FPY. So here's one factor. So if this factor is close to 1, what's going to happen? Just for curiosity here, if this is going to be close to 1. If I put pre-stress all the way equals to the yield strength, is this something good or is this going to be something bad? Yes, I'd like to hear from you guys.
Something good?
When you increase the pre-stress, amount of pre-stress, so you take this, divide by this. I have here two options. One option to go to 70%, the other option is to go to 100%. Would you go to 70 or 80% or 100%? Based on this equation.
70.
If you go here to 70%, this number, this factor at the end is going to be smaller, which means that you're going to have less losses. So someone's going to say, I'd like to go to 55% of FPY, correct? Because if FPI divided by FPY becomes 0.55, I'm going to have no losses, correct? Losses becomes almost nothing. But the code says here, don't go to any value below 55% of FPY. Look what I have used here. How much did I use of FPY? I use 82%. But I'm not going to be going to 100% because 100%, if you put pre-stress close to 100% of the yield point, this is going to be too bad because your loss is going to be high. As an engineer or manufacturer to this precast members, you'd like to go to higher values of FPI because you'd like to use this more efficiently. You don't want to throw the material there. So actually, you'd like to go to high trends, if possible, to go to 260, right? KSI, or maybe 265. But the problem, if you go to 265 and then you have any overload, you're going to be breaking or snapping the cable. It's not good. So you're going to say, well, maybe I'd like to bring it to maybe close to FPY. You're going to say, yeah, this is good. Let's just put here tension, not just 189. If the cable is able to take more tension, I'm going to be going here to 229. What's the benefit of doing this? Benefit, you're going to be reducing the amount of strands needed. And instead of putting, let's say, 7 strands, and you run the same numbers for the previous example or homework, maybe you're going to end up with 6 strands. So there's going to be less cost. So you'd like to put higher strength material, and you like to push it close to FPY so that you reduce the number of strands. You'd like to save money in this case. But we have this equation that says if you're going to be going here to 100% of FPY, you're going to have higher stresses and higher losses. So we said, let's make it here like 82% or maybe 70%. Once you get here to 82%, you're going to be at 189, right? So you're not really killing the cable by reducing the amount of stresses, and therefore you're going to be saying, hey, I have no relaxation, this is good, but I'm going to be using lots of cables here. You're not going to be doing this. So you're going to be somewhere in the middle. You're not really using the entire FPY and having lots of losses. In the same time, also you're trying to use this efficiently. You'd like to use the rebar efficiently or the strand efficiently. So, okay, good. All right. One equation, empirical formula. At least with this, I can figure out the amount of relaxation. And here's the equation again. And this is the discussion about using it of 0.55, because with this equation, just say FPI divided by FPY, it needs to be more than 0.55. Otherwise, this equation, you're going to be getting negative, which doesn't make any sense, right? So this equation valid when FPI divided by FPY is going to be more than 55%. And people decide here in this industry to use maybe 85%. I personally, I used here 82% in my analysis for the 189, which is about 70% of FPU. So we have here good room. We're not going to be snapping the cables for any overloads. This here, the second type, which is the low relaxation steel. This is going to be the 416. As I said, that we are going to have here two types. One of them is going to be stress relief. The other type is going to be low relaxation. And look what happened to my equation. This equation here, for this type of steel, the stress relief, this is the one that we heated it up and then we let it cool down. We have this component of 10. We have this factor of 10. So you take here log T, T is going to be the time in what? Is this in days or is it going to be in what? I'm just wondering, what is this T? Do we know what is this T?
Days.
Hours.
Hours?
Is it hours or days? I mean, anyone knows about this?
Hours. They
Does
said
it say
hours on
here?
that.
Okay, great. Okay, so it's going to be an hour.
Wow.
And then your denominator here, it says 10. This is going to be what? Which one is this? Again, the one that has 10, this is going to be the stress relieved. The low relaxation, look at what happened. It's going to be the same equation, but the factor is going to be 4.5 times. Meaning, if the losses here is going to be equal to 10, let's say the losses here, total loss is going to be equal to 10, this losses here is going to be equal to 10 divided by 4.5. So it's going to be much less. So the losses here is going to be about 15% of the losses there. So what is the benefit of, again, let me go back to this graph. What's the benefit of putting this tension while you are going to be cooling it down? You heat up the strands and then cool it down. What's going to be the benefit? You're going to say less losses. By how much? You're going to say the losses here is going to be roughly 50% of the losses here. Because it's going to be factor of 4.5 based on this empirical formula. You're going to have much losses, much less losses. Does it make sense?
So it allows you to have more stress.
Yes. So the losses here, let's say is going to be something. I'm going to say FPI, right? I'm going to say multiply by some factor divided by 10. Correct? Based on this equation. Our losses here is going to be equal to FPI divided by some factors divided by 45. It is worth it if you can use this. If this is available, the low relaxation, right? It's going to be great if you can use this, if it's available. Otherwise, you just stay with this and you know that you're going to have some losses that you need to live with, more losses. Again, the conclusion is based on this given two empirical formulas. This one here, denominator is 10, and this one here, denominator is 45. For the low relaxation, the yield strength itself is going to be higher because it goes to 90%. For the stress relieved, like what the code says, is going to be about 85%. So this here, this type of strains is going to allow you here to put more stress on the strain. But in our course, we're going to be using this type, which means I'd like to keep these values. So this slide would include the stresses needed for any problem that you're going to be doing, whether you do it in a homework, in your exam, in a quiz, it's going to be exactly the same values. We're going to keep it as 270, and you start to memorize this, right? 270, 189, and 150 for your design values. Any questions?
No questions.
Yes, go ahead.
Oh, I said no questions.
Okay, thank you. I'm sorry, I didn't hear you well. Disconnection. Look at the difference between the two. Here's the time in hours. At the same time, what happened for this low relaxation versus the stress relief? How many times the difference is? You can say careful because it's gonna be log scale, right? So it's kind of tricky. This is not like 1 versus 1.25 or 1.5. No, it's not like this. This is gonna be log scale. There's quite some difference.
4.5.
Yeah, about 4.5 according to this equation, this empirical formula, right? As long as you have FPI divided by FPY, it's gonna be more than 55%. Corrosion also is gonna be critical part. Just imagine that you have a strain, and in your analysis you assume that you have 0.153. Part of it is getting corroded. What does it mean? It means that the rebar itself is gone, or the strain is gonna be gone. So the effective force that you have in there is gonna be, of course, much less. It's gonna be based on the amount of loss that you're gonna have here in the cross-section area with the strain. If you lose here 25% of the strain size or cross-section area, it means that you lose here 25% of the force. So you don't want this to happen. This is why protection of the rebars and the strain is gonna be very critical in pre-stress. How do you protect it? It depends on the environment. If you have lots of chlorides, if you're close to the ocean, maybe you like to go to uncracked sections. So actually you can decide. If you like, you can decide, and then you can say, I want the structural precast members here or pre-stress members to be uncracked. I'm not gonna allow any cracking here. So this is gonna be your target criteria. No cracking in the structural members. You're gonna say fine. If this is the case, you need to be sure that the tensile stress that you're gonna have under this both of these two conditions, the initial pre-stress and the service case, that the tensile strength or stresses is not going beyond 7.5 square root of A prime C. So, okay, good. All right. How about if I'm allowing cracks? You're gonna say, you know what? Your limit is gonna be 12 square root of A prime C. But it's okay to go beyond 12 square root of A prime C, but you need to provide non-tension rebars, like conventional rebars. So it's allowed, it's okay. But you're gonna have rebars. Otherwise, the concrete is gonna open up and you cannot control it. So in this case, I'm gonna put here some reinforcing bars. How about in between? Yes, go ahead.
Sorry, do they coat the cables?
Does it coat it?
Yeah,
the
the
pre-stress,
cable?
yes, it comes in sleeves, like in something like the hose, like a sleeve, like conduit. You know the conduit, the electric conduit. It comes in very, yeah, and usually is going to be covered with grease.
But it's
And
not
also,
like the same kind of material, like they dipped the rebar, like the coated rebar, that green stuff.
Oh, you mean the epoxy coated? No.
Yeah.
No, they don't do it out of epoxy coated, because just think about it. How would you do epoxy coating in this strain?
Good point.
Yeah, I mean, once you start to put them all together, you start to twist them, you're going to be breaking all the epoxy. So if you coat them before you start to twist, you're going to be chipping off all the epoxy coating, right? You cannot keep it. And if you try to do this epoxy coat after you twist them, what's going to happen to this area here? Right? You cannot really cover it. So it's going to be a tough process. So what do? Usually cover it with grease. Usually it comes in grease. And certain rebars and tendons or strains, they come with no grease, but in this case, you're going to be grouting it after the fact. After you do the pre-stressing, you grout it. I guess we have seen some video clips on this, right? That you grout after you do the post-tension, you grout the space between the strain and between the conduit. So corrosion is bad again, and then let's go to this uncracked So if you wanted to consider uncrack, tensile stress cannot go beyond 7.5 square root of prime C. You allow crack, you put reinforcing bars. How about in the middle transition? You say, okay, in this case, you keep the tensile strength or the tensile stresses. You keep it between 7.5 square root of prime C to 12 square root of prime C. Top and bottom, at any place in the concrete section, at two conditions. One condition at the initial pre-stress, which means FPI top and bottom, right? You do the stress in the beam top and bottom at the time of the initial pre-stress, and then you do it again at the time of the service load. And in both of these two cases, top and bottom, the tensile strength cannot be going beyond this limit if you are planning to go to uncrack. So you're getting control. You can decide. Do you want it to be uncracked section or do you want it to be cracked section? You're gonna be okay with this. If you have this uncracked section, you don't really need to add conventional rebars to the beam section because you don't allow any tensile stress or tensile strain. It doesn't have in the concrete. You have enough strength and you have enough compression force and compressive stresses within the beam. So you should be good, right? You don't need any conventional rebars. In here, you may need some. In here, definitely you need. You cannot have it without non-pre-stress rebars. But generally speaking, if you decide to add non-pre-stress rebars to gain strength, this is going to be a different story. So based on the performance needed, if you want it to be uncracked, you don't really need rebars. Here you may need rebars, and here definitely you need rebars. But if this non-pre-stress rebars, you want them for the strength, so in this case, you can add into any one of these categories. It doesn't matter. Does it make sense or no? Yes? Yeah, okay, good. The terms and the symbols that we're going to be using here in our business is going to be F prime C, you guys know it. F prime CI is going to be the initial pre-stress, right? And this is going to be the value that you'd like to check before you start the pre-stressing process. So for example, in your analysis, you decide that the F prime CI is 4,000. So in reality, you cannot really apply the tension for the pre-stressing before you gain 4,000. Otherwise, something wrong is going to happen, right? F sub y is going to be the trends for the conventional rebars. FPY is going to be the yield trends for the cables or tendons. FPU is going to be the ultimate. PI is going to be the initial. FPE is going to be the effective pre-stressing. So I put this slide here, so it's going to include all the symbols that you're going to be using in your analysis. How about the code limits? I'd like to have a standalone slide for the code limits when it comes to concrete stress. This slide here is about the allowed stresses within the concrete, whether it's going to be tension or compression, right at the time at the initial pre-stress, immediately after pre-stress transfer. Also to confirm this, once you see here F prime CI, you're going to say initial pre-stress, right? At the time of the initial pre-stress. This value here, it says end of simply supported in compression. You have 70% of F prime CI. The one that we used, if you remember, in our example was only 6%. Am I correct about this? Should I put it back? Was it 60%? Anyone recalls this? Previous example.
Yes.
We used 6%. I didn't try to use 70%. This is the value I put there. I said this can be the limit from where we set the code. Now I'd like here to go and confirm this with the code. This slide is going to be only about the allowable stresses at the initial pre-stress. So anytime you'd like to check here the stresses right after the pre-stress, which means at FPI value. What is FPI value again? I'm going to go back here just in case. FPI, when you are at 189, when you have only the dead load, you don't have the additional dead load or superimposed dead load, and yet you don't have the life load. So in this case, it's going to be the allowable stresses in compression, and this is going to be usually the value that we use. We just ignore this. We say, you know what, let me just keep it at 6%. Easier and safer. Would come to tension is going to be 3 or 6 at the end, square root of A prime C. So I was going to say, how about this 7.5? I'm going to say, look at this 7.5. What is this about? This is going to be at the service load, right? So, okay. But during the pre-stress value, I don't want to crack the concrete. Otherwise, I'm going to be losing it. So we're going to keep it at 6 or 3p square root of A prime CI. So again, looking for the allowable stresses right after the pre-stress, the instantaneous pre-stress, or applying the pre-stress force. This is going to be the limits of the code. Now you're going to be saying, where does this come from? Can I see it in the code? I'm going to say, yes. Look at this. Here's the code section. Just copy and paste of the section, of the code section. So this slide, just go with this slide. Use any one of these two, whichever you like. This is going to be the same information. 70 and 6%, 6 square root of A prime C, and 3 square root of A prime C, and of course, it's going to be A prime CI at the time of transfer, initial pre-stress. How about at the service level? I'm going to say service level, I'm going to have exactly the same. Here's the service loads. It's not going to be about F prime CI. It's going to be about, if you remember, just F prime C. It says here 45% and 60%. You can say, you remember this? In the solved example, we use 45 F prime C, right? This is where it's coming from. It says here, when you have the pre-stress and sustained load, what is a sustained load? Sustained load, which means additional dead load, is going to be 45% F prime C. For the total load, it's going to be 6%. So actually, the code here is asking me to do 3 checks. I thought it's going to be only initial and total or service. They say even for the service, we can do it in 2 phases, if you like, or 2 steps. The first step, when you just apply the additional dead load, but there is no use yet. And then you check the stress, it says it's going to be about 45%. And after you add the life load, it's going to be maximum of 70%, 60%. Some people would say, just make it simple and do the check based on 45% for the entire load. If it passed, so this, I mean, there is no need here for me to do it for the total. So if I do it for the total, I'm going to be within here 45%, I'm good, I'm free. I don't really need to do additional check. So what people usually do, they're going to be looking at the total stresses and try to compare it with 45% first. If it didn't work out, they go back and look at only the sustained. But if you're using a software, it doesn't make any difference, right? Because the software is going to be checking for any load combination or any load cases you want it. You can divide it the way that you want it. Now, at the service case, you can have it as uncracked, or you can have transition, or you can have it cracked. You remember this issue here? Uncracked, transition, and cracked. I'm going to say, yeah, it's right here. And this is going to be only for the service. So be sure that you remember this. Look at this. It says here, at service loads. So this uncracked versus cracked is going to be only a service check at the service loads. It's not going to be about at the pre-stress, initial pre-stress. So okay, also I have it here, just in case. This also copy and paste from the code. So you have the source of it. So I have here 4 slides. The first one about initial pre-stress and the source of it, service, and the source from the code. Any questions? You're good?
Yes.
All right. Where did you get this 70%? I guess I was just talking about the 70%, right? FPU. I need your help here. Can someone take the 270 multiplied by 0.7? Tell me how much is that?
189.
Great. Okay, here we go. Just gonna go back, take you back here. Oh, it's right here. See the 70%? 189. So I guess now you know where I get the 70% from. It's gonna be from this code section, and you have here's the source of it. You'll be immediately at time of force transfer. Okay. What is this? This can be about Caltrans bridge design specs, and they have different method of handling the concrete stresses at that level. And I just put it here for you, but I'm not going to be using it because in our examples, we're not going to be doing bridge design. We're going to be doing, I'm going to see here conventional double T's and beams and so forth. So I'm not going to be doing a bridge design example. But I just put this just in case if someone here is going to be talking about bridges, so we know that we have different information, a little bit different information. It should be almost the same because look at this, what happened here. 45% and 6%. And I guess this is all taken from the ACI. You see this 45% and 6%, I'm gonna go back here. Where is this 45 and 60? It's gonna be the same. But when it comes to some other values, like in tension, they have different requirements. So I'm not gonna go there, right? But in compression is almost the same. Any questions? I'm done for today. If you have any questions, go ahead, please, and ask. If not, and you'd like to leave, go ahead and sign out.
Thank you.
Good night. Thank you.
Thank you, Professor.
Thanks.
Thank you, Professor.
Thank you.
Hey, Professor.
All right. Good night.